Okay, this is a little bit more this is a little bit more less theory. This is more just a bit of a fun thing that exists in the world than some of the other talks we've had. So, what is Kryptos? Kryptos is a puzzle that's it's in the CIA headquarters. It's been there since the 1990s. It was commissioned by I can't remember his name. Jim Sanborn. That's it. For the CIA headquarters. It's a series of 4 puzzles. So, puzzles 1, 2, and 3 have all been solved, and they were solved back in the 90s. Puzzle 4 is still an unsolved mystery, and no one knows how to solve it yet. So, what we're going to talk about, we're going to do a bit of how to brute force classical ciphers, how we score ciphers, and how English is something. Because it's quite a hard thing to quantify, so how can we tell if something is English? We're going to go through breaking Kryptos 1, 2, and 3, talk about why it's important, and then talk about how you'd go about solving 4 and how people have tried, but we're not actually going to get to a solution because I've not done it. So, if I had, it would be great. So, could we just try all the keys? Would it work? Well, let's just suppose we have a substitution cipher. Basic, one letter goes to another letter. The issue is, we have 26 choices for the first one, then 25, then 24. If you've done some A-level GCSE maths, you know that ends up with 26 factorial. 26 factorial is a very big number. It's more grains of sand than there are on Earth. It's more stars that are in the observable universe. So how can we go about trying to find something, find that one value we want in that massive space? So let's just try and brute force this a second and see what happens. Let's see if this breaks when I try and alt-tab out of this PowerPoint. Let's try this. You can't see that. One sec. Windows P. Here we go. Duplicate. Here we go. So this is just a basic script. All it's going to do is it's going to basically randomly try keys for 30 seconds. And we're going to see how many it does. So all it's doing is running the decode on that piece of text. And then it's waiting to see if it hits the time and adding up to a counter. 30 seconds feels longer than I thought it would. Yeah, well, I ran it earlier. It's fine. Oh, you can see that now. Extend. Voila. So I ran this earlier because we're not waiting the 4 minutes it can take to run all of those. So on average, you can run about 5-6 million in the 30 seconds I let it run, which is about 167,000 per second. So, this is also in no way optimized. This is just I threw this together in 10 minutes. So you could fully get this so much quicker, but this works to illustrate what we're trying to illustrate. So that's how long it would take in years. So to put that into context, the age of the sun is 4 trillion years. Is that trillion? Billion. The age of the universe is 76 billion. And no, 70. The age of the time it will take to brute force that is 76 trillion years, which is 5,000 times the age of the universe. It's not feasible to try all of those. So we're going to have to try and do something else instead. We're going to come back to that in a minute and take advantage of some stuff. But how can we tell how English something is? So by looking at frequencies and letters, we can kind of see how English is something. But if we just take one letter on its own, if you look at the frequencies of the English language, E is going to come up a lot and A is going to come up a lot. So we run into the issue of actually that is probably the most English text you'll ever see according to those statistics, because that is just pulled straight from the statistics. So how do we get around this problem? Instead, we're going to actually start looking at groups of letters. So rather than just taking one letter, like A, we're going to start looking at maybe blocks of 2 letters, or 3, or 4. So, and then we're just going to score them exactly as we did before and compare how many of them appear in the English language. This is called n-gram analysis, and an n-gram is just like a block of n letters. So monogram is 1, bigram is 2, trigram, and so on and so forth. So it tells us much better how the text is composed rather than just telling us about, it tells us what letters go next to each other. So the trigram the should come up a lot more than the trigram of 3 Zs next to each other. So this is, if you run the scoring algorithm for a basic substitution cipher, you can kind of tell which one the answer is here. It's the big one with the 13. So these are logarithmic scores, so I've taken the exponential of them just to make it look clear on a graph. So that big one, that's what the actual answer is. So that's the one that's most English, because most other text, when you run it through a cipher, will just look like random data. There's going to be no statistical significance to it. So that's why you've got all these other little ones. And the one that is English, it has all of the right groups in it. So therefore, it looks like English according to the scores. So, in Kryptos, in the puzzle, there's 2 bits of the puzzle. There's the big bit of ciphertext on one side of the puzzle. And then on the other side of that sculpture is this. This is what we call a vignette table. The vignette table gives us a hint to what at least some other ciphers are going to be, because it's used to do one major. But there's a difference between this and a standard vignette table. This begins with a keyword at the top. So this begins with the keyword Kryptos, which is the name of the puzzle, which is where the puzzle gets its name. So that, we offset our entire alphabet by that and then just keep putting the letters in. So this makes the puzzle a lot harder to solve because we can't just do the normal analysis we do, because we need to offset by the alphabet and handle that. So, a vignette cipher, I'm going to go through this for, just so everyone knows. So the vignette cipher is basically a load of rotation ciphers together. So we're going to offset the letter H by the value of K. So like K is the, I don't know what letter in the alphabet it is, but K would, like A would be 0, B would be 1. We're going to offset it by that much. So you get that out at the end. And then when you get to Z, you wrap back around for start. But instead, in Kryptos, because we're offsetting by this different key that's not our alphabet, we're going to have to, the mappings work out differently. So actually K is our 0 shift, R is 1. So if your key is 1, you shift. If your key is K, you shift by 0. Your key is R, you shift by 1, and so forth. So, how are we going to try and break this? So this is where those statistics we came into earlier. So, we're going to go and try a load of keys. But because we're going to take advantage of the fact that if we get one letter right, that's going to give us the text is going to look better than if we get 0 letters right. So that is what allows us not to have to go through all 26 factorial combinations and allow us actually, I think it's 26 to the n instead, which is a lot easier to go through. So we're going to start off with our basic key, which is going to assume it starts all A's. And then we're going to go through and find the best value for the first letter, move on to the next letter, find the best value for that, move on, and keep going through, go back to the start. We're going to keep doing that until we don't find any improvements. When we find no improvements, we're going to start, and we assume that's our best key. There are some issues with this, that you might find local maximas, but how you get around that is you just randomize your start key and run it a couple of times. So, this second demo, let me just load it up in VS Code. So, this second demo is just going to run the decode for both Kryptos 1 and 2, which both use the vignette cipher. But when I run this, we're going to notice something. The second one is going to give us a key that we're somewhat expecting abscissa. And that's because we've actually got a much bigger key space, or a much bigger text. So actually the statistics work. For our small text, so the Kryptos 1 is only 75 characters, that is actually not enough information to be able to do the statistics. So actually K1 is a lot harder to solve. You've got to do a lot more work, you've got to start in different places, and run it many times to actually get K1 to work. K2 is much easier to get to solve because it's got much more data for us to go through and like do the statistics on. I need to go back to my PowerPoint now. There, cool. So, K3 is a different kind of cipher. So K3 is what we call a transposition cipher. So actually, we're not going to change any of the letters anywhere in the text. All the letters that go in at the start come out at the end. We're just going to move them round a bit. So as you can see from those graphs, there are two graphs at the bottom. There's the one on the, would be your left, is all of the stats look fairly similar to English. So that will kind of give us the hint that that's a transposition cipher, because you can see that we're not changing the frequencies of the letters. Whereas this one on the side is a rotation cipher. Well, I think that's what it is. And it's changing the frequencies of the letters, so you can see that they're changing. So it's not a transposition cipher. So how did they go about? We're going to go about breaking it in a slightly different way in a minute, which only works with more compute power, and now we know the answer. If we didn't know the answer, the way we're going to compute it doesn't work because someone worked it out. So breaking a transposition cipher is mainly just a sequence of guesses, because things come up in English a lot more. Like the words "the" come up a lot more. The letter Q tends to be followed by the letter U. Patterns like this in English, like where you can kind of go, okay, if we know this is going to come out, we're using 8 columns, and we're going to have rearranged those columns. Actually, we want to kind of try and group the "thes" together, because if we get all of the words like that is TH and E together, they're probably going to be together in our thing. So they went through and they did this for small bits of it, and as you start doing small bits of it, you build up to your full solution. So you get like the word "the" here, the letters Q and U together somewhere else, and then eventually you build that into your full message. The interesting thing about transposition ciphers is actually because they're just a mapping from one thing to another. So there is no one solution to any of these problems. Or there's a solution, but there's no one way to get to that solution. So there are 3 ways that people have found to map all of the letters in Kryptos 1 to the Kryptos 3 to the answer. We're going to look at one of them here. So this, you'll see that the text gets cut off, but that's just because it gets too long and I decided to crop it off. So first we're going to put that text. That text works out exactly to fit in a 24 by 14 grid. We're then going to rotate that grid. So the letters on the top are going to go down the side. So the E and D here go down the side. The letters on that side are going to go to the top. We're just going to rotate that entire table 90 degrees. Then we're going to change it into a column of 8. And then we're going to rotate that again. And when you do that, that has the same mapping as all of the other results. So we're just applying a transformation to it. We're doing some set of operations, and that is just going to give us, out at the end, this, which is a quote from a book, I think. So, why is Kryptos important nowadays? You might think that, it's classical cryptography, it's not really useful. Well, even though K1, 2, and 3 have been solved, K4 remains unsolved, offering a mystery for people that just want to get into the hobby, just want to learn things, and get to engage with people. It allows a great collaboration between different communities. So you've got our intelligence services. So the first people to solve, some of the first people to solve the Kryptos puzzles were the NSA, and they then worked with other people to try and solve K4. So it allows the hobbyist communities and the intelligence communities to kind of get together and do something to kind of be more open with each other. And it shows that even though it's a classical cipher and it's just doing some basic operations, actually, some of them are quite hard to solve. Like, we've not managed to solve K4 yet. So it shows there's a resilience there to these things. And one interesting thing. So this at the bottom comes to the National Cipher Challenge, which is a competition run by, I don't know what uni it is, but it's one of the unis, for A-level students. So it's a good way to get, Kryptos is a good step above that, because in that competition you're learning things, but you kind of get to find out the solutions, and you're kind of working on your own. Whereas Kryptos is kind of gets you, there's more of a community around it, you can work with other people online to try and solve them, and just work generally and get more into the cyberspace. So, over the 35 years since the puzzle was installed, people have tried basically everything they can think of to try and solve it. Some people believe that K4 is going to be a combination of the previous two, so you're going to need to use stuff from the previous three to kind of solve it. It might be a vignette and a substitution and a transposition cipher together, or something like that. But there's also, around the puzzle was installed a load of like random things. So there's a compass, there's Morse code in the bricks, there's a load of other random stuff next to it. So there's lots of people that reckon that those things are going to be the key to solving the problem. So, this is an interesting one. So, we know part of the text. The guy that created the puzzle, in 2019, released this section of it. So we know that the word Berlin exists in the third line, and in the second line, there's east-northeast, which is a direction. So we know that these exist, but they've not actually helped us any in the solving of it, which is very odd, because cribs are normally really useful. They are the underpinning thing behind most of classical cryptography. So that's how you break Enigma, that's how you break Lorenz, the ciphers, and they're the ones you use in the war. So you use the fact you know bits of the text to work out how to solve it. And that, I think, is the end.